The trick I've shown to you here always works. If you get the polarity right and you're able to write the equation starting from a point and going around the loop like this, you should be able to do it fine. Yeah? So I'm just going to clear this one and now write an equation for the output side. So again, I'm just going to put the direction of currents again. So this one was like this, and this one was like this, and this one like this. Okay. Now, as you go from, you're trying to go in this direction now. This is the output side. Okay, so you're going to do this loop. So again, we start on ground. We go from here to here. Now, like we said, the base collector junction is not forward biased, so you can't put 0.7 there. So we'll call this one VCB or VBC, up to you. Yep. So we're going to call this voltage across base and collector, which is actually reverse biased. So it's not 0.7. So let's call it VBC. Now, can you try to think about the polarity VBC would have? If you start from here, you're going across to this side. Can you see this is grounded, but the collector is connected to a negative terminal. So when you go from this point to this point, you're going in the direction of reducing potential. So convince yourself about this. As you go from the base to the collector here, because you're moving across this loop, you're going in the direction of reducing potential. Yeah. Since it's reducing potential, you have to put the minus sign. So minus VBC because base is at ground, but the collector is at the negative terminal, as you can see here. So as you go from base to collector, you're going in the direction of reducing potential. When you go in the direction of reducing potential, you have to put the minus sign. Now, next component you find is you have the 10K resistor. So this one is IC, the collector current. Now, just see the direction of current. You're moving from here to here, and you're moving in the direction of a current. So if this is the current is flowing from here to here, it means you're going in the direction of reducing potential because current always flow from high potential to low potential. So as you go across the resistor there, since it's the same direction of current, it's a negative sign, so minus IC times 10. You're going in the direction of reducing potential. So same comment here, I'm not putting the K, assuming that IC is already in milliampere. Yeah. So if you want to put the times 10 power 3 there, then you would get your current in ampere. But if you do that small trick there, means you know already that IC would be milliampere. So we started here, we've got minus VBC, and then since you're going in the direction of the current, so reducing potential from here to here, you put the minus sign. Now, next thing, you're going from here back to your ground. So this is the negative terminal. As you go across your battery, you go from negative to positive. So you're going in the direction of increasing potential. You're going to put a plus 25. Because direction of increasing potential plus 25. The sum of this has to be equal to 0. Okay. Now your aim is to find VBC because this is the voltage you want to find. You can assume now your IC, since in this question alpha is not given, because like we said, alpha is not given. Alpha can be assumed to be approximately equal to 1. So the value you got for IC, for IE, you can assume this to be equal to IC. But as we mentioned earlier, the base current is very small. You can assume to be almost 0. So if your alpha is not given in a question, you can assume it to be approximately equal to 1. So the value you got for your IE from this one here, you can just replace it there, and then you get your VBC. That's what's done down here. I'm just going to scroll down here. Exactly what you've just done here is given in your handout. And since now we are assuming that your IC is equal to IE, and we got IE from the input side to be 0.465 milliampere, just plug it there. So you're getting a V, it's written VCB here, you can write as VBC, doesn't matter. But important is a negative sign that you have to put in front of it because your base was more positive than your collector. So you're getting now a VCB of 20.35 volts. Okay. Yep. So there are more examples given there. So I'm just going to guide you through them, but I would want you to be able to, the small mistake there, it's not an equal to sign there. So I've written the equation again as a comment. Yeah. So actually it's a minus sign. Okay. So when you're solving the problem, just pay attention to this. Let's just look at these two circuits there, and I will not explain in detail like I've just done. I would want you to go through this on your own now and convince yourself. So whenever you get a circuit like this, the first thing you have to identify is where the emitter, base, and collector are. This is the emitter because the arrow is on here. So this is the emitter, this is the base, the collector. There's a common base circuit again. But what type of transistor is this? As you can see, the arrow is going into the emitter. So it's an NPN transistor. on this one, you can see arrow is going away from the emitter, so it will be a NPN transistor. So this is an NPN transistor. So I'm doing a small mistake. So this one is an NPN transistor. If I just write it down. So this one, we're saying, if you look at the arrow is going into the emitter, so it's an NPN transistor. And you can see this one, the arrow is going away from the emitter, so it's a PNP transistor. Yeah, so we explained why earlier. Now, once you've got this right, you're going to find that the middle letter here is P, so positive, P for positive. It means the collector and the base would have to be more positive. So it is correct, plus 20 and ground, which is more positive than minus 10. This one now, the P and P, so N is negative in the middle there. So the collector and your base would have to be more negative than the emitter. So minus 20 and 0 for the base and minus 20 for the collector. It is more negative than the emitter. So it is correctly biased. If a transistor is not correctly biased, it's useless to solve for it. You can just stop there and say it's not properly biased because your transistor will not work. Yep. So the first thing you need to do in a transistor circuit is to check if it is correctly biased. So we've done that. So next step, you're going to draw the current. So the current here for the emitter is going to be this direction, and then the base current is going to go in, and this one in. And then you will write an equation here for your input side. So start from ground, go up, check with the polarities. When you come to minus 10, you go back to 0. So in this case, if you are following this direction here, when you go from minus 10 to 0, you're going from a negative potential to a higher potential. So you put plus 10 for this one. Same comment for this one as you go from ground and you go up. Yep. So you're going in the direction of increasing potential. Write the direction of current, of course. And then as you come to minus 20 and you go back to ground, since now you're going from plus 20 to 0, you have to put minus 20 because you're going from a high potential to a low potential. Okay, so in this diagram here, you will have to draw the direction of current. So the emitter is like this, and the base and the collector would. So if this one is going in, it's going to go in here and in. This one is going out. So this IE is here, going out. So this one would go out here and out. So once you do that, then the answers are here in front of you, but you would have to convince yourself they're right. So I would want you to give it a try using the method I've said earlier. You should be able to write them. This one as well, so you can give it a try. There are lots of work examples in your handout, so to give it a try. This one would be, if you look at the transistor here, so you can see the direction of the arrow is into the emitter. Yep, so into the emitter is an NPN transistor. Yeah, NPN transistor. The P is standing for positive, so the collector and your base have to be more positive. They are more positive here. This configuration is called common emitter configuration. As you can see, the emitter is common, is between base and the collector. So in this case, the base current is input and the output current is IC. So again, you have to draw a direction of current. So if that's the current is flowing like this, if so, your base current would be going into it and the collector current into it. And once you do that, you're going to write two equations, one for this side and one for this side. Now, bear in mind, like we've concluded, the base emitter junction is always forward biased, so you have a 0.74 drop across it, whereas the junction between your emitter and the emitter and the collector in this case would not be 0.7. So just put it as VCE and just solve for it. This is the aim of the exercise. Is once you have got the equation to the output side, you can find the output voltage, which is across the collector and the emitter in this case. Now, can you find a beta value is given in this circuit? Yep. So beta value we know is beta is going to IC over IB. As you can see here, the collector current is output and the input current is IB. So once you found IB from the input side, when you multiply your IB by 100, you're going to get IC. Yep. So in a way, this ratio here allows you to relate your input current to your output current. Yep. So once you've got IB from the input side, you can multiply it by 100 to get your IC. And then once you get your IC, you can find your IC. So all the workings are given there. So, but I would encourage you to be able to write them on your own. That's very important. Okay. So I'm not discussing this in detail. This one will be your tutorial sheet, which I will send to you. Yeah. So you can work it out. Now, next topic, which the last topic actually, which I want to discuss on transistor is something called operating mode. So till now, you already know how to solve. So if I give a circuit like this to you after some practice, you'll be able to calculate the input current and the output current for me and find the suitable voltage. In this case, with VCE, you're able to find this out. Now, what's the whole purpose of this exercise? If we consider this circuit there, yeah. So if you want to write an equation, not solve for values, but an equation for the output side, yeah. So this is the equation for the output side, yeah. So if we start here and we start going up, we find that you have a VCE across it here, yeah. So you have a VCE, and then you would have an ICRE, yeah. So because the current flowing in this path here would be IC times RE. Sorry, it's not RV here, it's actually RC. It's a mistake because we don't have RV here, so it said RC. So actually this one. Let me just put a comment there. Small mistake. Just put a comment here. So this one actually is RC. Yep, it's IC, RC. Yep, we don't have RE in this circuit. So I'm just putting this one there and just pay attention. So again, this one there would be IC, IC, RC. Okay. So as you're reading through this, make it this changes. Now, once you are able to, so let's start again. You start from this point, you move up, so you get VCE, and then plus because you're going from you can see current is flowing down here. So it means the potential from going here to here is rising because current flows from high potential to low potential. So plus ICRE. When you reach on top there, when you go from VCC to ground, is minus VCC. Yeah. So this is the equation for the output side. If you do a bit of reshuffling, you find that VCE is equal to VCC, if you send it on the other side, minus ICRC. This is what you get. So let's just analyze this equation there. In that equation, you have two parameters which can vary. VCC will not vary, that's the voltage of your collector. RC would not vary, that's the resistance there. But the two parameters VCE and IC can change. Now let's see what different possibilities we have. The first possibility is when the transistor is switched off. So it's called a cutoff, means when IB is 0, IC would also be 0. Yep. So in case your IB is 0, your IC would also be 0, like I mentioned earlier. IB, even if it is 0, it's a very small current, it's fundamental to have an IB so that the transistor actually works. So if your IB were to be 0, your IC would be equal to 0. So in that equation there, if you make IC become 0, you're going to get VCE is equal to VCC. Means when the transistor is not operating, which we refer to as cutoff, yeah, cutoff, your VCE would be equal to VCC. That's one condition. Now, the second condition is what the maximum value IC can take. So the maximum value which IC can take, if you look at this equation there, is when VCE is actually equal to 0. Yeah. So if you put a value here for IC, and then you have to find IC from it, you're going to subtract. So if you just do subject of formula, you find IC is equal to VCC minus VCE. So if VCE is actually equal to 0, that's a case where your current IC becomes maximum. And this is called a case where when your IC maximum is called saturated. So it means this is a point where the transistor is at maximum current. So one case is where IC is 0, that's called cutoff, means it's off. There's another extreme now where IC is a maximum value. This maximum value occurs when VCE is equal to 0. In that case, your current IC would be equal to VCC over RL. Just replace there, just replace VC by 0. You find IC is equal to VCC over RL, over RC. Yeah? So this condition there is called saturated. So it's a limit of saturation. Now, this table summarizes very well what I just explained, the different modes of operation. So the first one we mentioned is when the current is 0, it's called cutoff. Okay? The next condition is when the IC is maximum, then you get it's called saturated. This is the point where it is at the maximum current. And then between these two now, between a value of 0 and this maximum value, you have a linear region where the transistor can work. Yeah. So this one is called well saturation. We actually never get there. Yeah. So you can't exceed it. Now, if you plot a graph now, this is a graph to show it's called a DC load line. So this is showing all the possible combinations of the current IC and DC which you can have. If you look at this equation there, which you have, it's the equation of the form y is equal to mx plus c. Yeah, where you can see your IC is one variable. Yeah, and the second variable is VCE. Like we mentioned, your RC and your VCC are all constants. The VCC is the voltage applied to your collector, and your RC is just a resistance. So these two can't change. What can change in this equation is IC, the current flowing in the collector region, and then VC is the voltage across the collector end to end. Yeah. So if you plot a graph now, you're going to get a straight line. One's going to have expressivity. So in this graph, you can clearly see the different regions. What we've seen here, IC is plotted in this case on the y-axis and the VC on the x-axis. Now we've mentioned already. So when your IC 0 is 1 here, and then you get a maximum. Your VC is VCE. So your VCE is equal to VCC. Just mentioned about this. So again, when your IC is equal to 0, means your transistor is not operating. This is when IB 0. So when IB is equal to 0, IC would also be 0. Your transistor is cut off, means it's off. In that case, your VC is simply equal to VCC. Just replace the equation, you get it. Now, the other extreme is when your IC is maximum. This is called saturation. So the value for IC max is VCC over RC, and this occurs when your VCE is equal to 0. This is the line where VC is 0. Yeah. So you get VCC over RC as the maximum value for IC. This is called saturation. Now, between these two extremes here, being off and being saturated, you have an active region where your transistor is operating. So it means you would have a value of IC which is not maximum and not 0. So when you solve now your specific circuit, what we've just shown to you is the whole possibilities of IC and VC. Well, now when I start fixing VB, VBB, VCC, and start fixing RB and RC, I would have a specific point where the transistor is operating. That point would be somewhere along this line, and that point is called an operating point. Okay, so the DC load line gives us all the possibilities that your transistor can operate at. You get this line by writing an equation for the output side, and then from there you can find the condition where IC is 0, this is cut off, and the other extreme is when IC is maximum, is when VC is equal to 0. Yeah. Now to know exactly where your transistor is working, you would have to solve the input side that you know how to work now. So you solve the input side, you find IB, you multiply IB by beta, you get IC. Once you know your IC, then you can locate your operating point where you are working on this curve. Okay. Now this is also called a quiescent point or the operating point. Okay. So let's take an example to illustrate how this works. This is the last topic I would want to discuss in your in this chapter on transistors, and this is a very important point. So this is a very important topic of transistors because you'll be asked actually to solve for your circuit to set operating or the quiescent point. So you know where transistor is operating, and then there's one calculation you have to do now. If you connect an AC supply and AC signal to your transistor circuit, how it behaves. So I will come to that in a few minutes. Let's take an example to illustrate this. So here you can see we are not putting here RC or we're not putting RB. Here we're putting specific values. Means using the specific values there, you'll be able to find your exact operating point. Before you can do that, you will need to draw your DC load line first. Like you see. So how you draw a DC load line? As you can see, first thing is this is an NPN transistor. Yeah, because you can find the arrows going into the emitter. So NPN transistor, PCs in between. So the collector and the base have to be more positive. They are more positive than the emitter. So it's correctly biased. Next step to be able to draw your DC load line, you would have to write an equation for the output side. So this is already done for you here. Why the 0 here? Because you don't have any resistor in this part. Why 0? And then when you come here, you're going from a point of 0 to a positive potential here. So it's plus VCB. So that's between these two here. Okay. As you go from this point up, you can find the current is going down. So this potential there would be at a higher potential at this point. This is why it's plus IC times 5. So it's a drop across your resistor. Yeah. And then when you reach 20, you have to go back to ground. So when you go from plus 20 to 0, you have to subtract 20 because you're going from high potential to low potential. So when you have been able to write this equation for your output side, you have your DC load lines. So as you vary your IC from 0 to maximum, you get your DC load line. So let's look at this equation there. The cutoff point is when IC is 0. It means your IB is 0, your IC will also become 0. So when you set this one to 0, you get VCB is equal to 20 volts. So on your diagram there, your VCB would be 20 volts at cutoff. You get this point already. The next point you need to find out is where is IC maximum. So if you look at this equation there, your IC is maximum when your VCB is 0, if you set this value to 0, because only two things can vary, or either a VCB or IC. You set IC to 0 to get the cutoff. That's fine. Next, you set VCB to 0, you get the saturated point, and you get an IC of 4 milliampere. Means 4 milliampere is saturation, so maximum value that IC can take. So on your DC load line here, you have this point, 20 volts for VCB at cutoff. You have 4 milliampere for the saturated maximum current of IC. Then you have a DC load line. So you have already drawn your DC load line. Next thing now in the question is mentioned is locate is quiescent point, means where on this DC load line are you actually operating. So how we do that? Now you have to solve your input side. So you have to find ID. So you start writing an equation for your input side, which we've seen earlier how to do it. It's done here already, bearing in mind that you have the 0.7 volts across your base and your emitter waves, because this junction is forward bias. So this is the equation which you have, it's minus 0.7 and so on. So I leave that to you, Shiva, to write this equation. From this equation there, you get a value of IE, okay, of IE to be approximately 2 milliampere. I've said neglecting VB there, it doesn't make a lot of difference if you take the minus 0.7. So the value is actually slightly less than 2 milliampere, but we have neglected it here. And we have made an assumption here again that your IE is approximately equal to IC because there's no alpha given. Yeah, your aim is to find IC because your DC load line has IC. So once you find your IC, IE, if you don't have any alpha given, you can assume IC to be approximately equal to IE, like we say, because IE is the reverse value. So we get around 2 milliampere for your IC, and then you can replace now this 2 milliampere in your output equation. You can very easily solve. If you place 2 milliampere here, you get VCB of 10 volts. So it means you are actually operating at 2 milliampere and 10 volts. This is your operating point. So this is your DC load line showing all different possibilities you can operate at, from cutoff to saturation. The specific point you're operating at is actually here. So 2 milliampere 10. What has set this operating point are these values of the resistance. So if you start modifying these two resistances there, you can actually move along this line. Okay. Now the last topic I want to discuss here is this thing you find here. Yeah. So what you've been doing till now on a circuit like this is you have considered only the DC biasing. So what's called a DC load line. Now, what if you want to connect now an AC to this transistor? So how is it done? I'll just show you how it is done, for example, here. So once you have done your biasing for your transistor, you're going to connect a capacitor there. The capacitor sits between your AC and your DC biasing you've already completed. This capacitor ensures that this biasing you've just worked up is not disturbed. Because we know a capacitor has infinite impedance for DC, yeah, because the impedance of a capacitor is 1 over 2 pi XC. If you've come across this equation before, so XC is the impedance, or if you want the equivalent of the resistance, the impedance of a capacitor. So the impedance of a capacitor XC is equal to 1 over 2 pi XC. So if you are working with a DC, the F becomes 0, so it's 1 over 0 becomes infinite. So it means the resistance to a DC offered by capacitor is infinite. It means this DC biasing you created cannot actually move across the capacitor here, but the AC signal can move into here because an AC signal would have a frequency. 1 over 2 pi FC would not be finite, it would have a value. So by putting this capacitor here, you're able now to send an AC signal to operate your transistor. Nothing complicated here. What we are showing here is what are the possibilities you can have, because when you start connecting, very important, when you start connecting an AC to your transistor, the AC is varying, it won't be a fixed point. Now what this is showing here is if you want to operate your transistor in a proper way, means you don't want the transistor to go beyond saturation or into cutoff region, because if you allow the transistor to go beyond this, it's going to cut off, the transistor will switch off, you won't get a sign. Yeah, it's going to be clipped. If you allow your signal to go beyond here, it's going to be clipped because your transistor is switching off. Same comment, if you allow your transistor to go on this side into saturation, it's going to be clipped. If your signal is being clipped, it means you are distorting your input signal. If you apply an AC signal to your circuit, you expect to get an AC signal which is amplified. So as you can see there, this is your DC load line as we've seen earlier. The This is your dyne. Okay? If you operate at this point, midway between the two, you have the maximum swing possible. Yeah, so you can see the swing here and the swing here is maximum. What if you are operating at this point? You can see the swing is smaller now, because if you allow, you can tell me on this side, yes, we can go all this extent there, but if you allow your swing to go on this side, it will go on this side and go into cutoff. It means now you can clearly see the maximum amplification you can have for your voltage is limited, because the operating point is close to your saturation. Same comment here. If you are operating your transistor at this point, the swing you can have in your AC is only this amount. If you allow it to go beyond, it's going to be clear. So as you can see here, if you want to get the maximum swing, the maximum peak-to-peak voltage in your output, the best point to operate is in the middle here. Then you have maximum swing on either side. That's all. So once you've done your DC biasing, you've set your point. This point is not always here. It could be anywhere along the line. But if you properly set the operating point in the middle here, like we've just seen, you will get maximum swing in your output. Okay? You get maximum swing in your output.